Permutation matrices. In this video, we're going to see the matrix view of swapping the order of equations. Consider the following system, which has neither upper triangular nor lower triangular form. However, by simply reordering the second and the third row, we arrive at the lower triangular equations. If we write both systems in the matrix form, on the left side, we see the initial system, which does not possess any special structure, and on the right side, we see the triangular form. It is interesting that we can achieve this result by simply multiplying both sides of the equation by matrix P. That is, if we multiply P from left by the initial coefficient matrix and P times the right hand side, this will result in the new coefficient matrix, which has the lower triangular form. We do the calculations. P times the initial coefficient matrix produces the lower triangular coefficient matrix. We call P a permutation matrix. We can verify this in Julia. We define our coefficient matrix on the right hand side and our permutation matrix, and we multiply P from the left, and we arrive at our lower triangular matrix. The key insight is that P is constructed from the 3 by 3 identity matrix by simply swapping the rows that we wanted to rearrange in the equations. This observation works in general. For example, consider this 5 by 1 vector. We want to rearrange and swap the third and the fifth rows. We start from the 5 by 5 identity matrix and we swap the fifth and the third rows, which results in our permutation matrix. Now we can verify this numerically in Julia. We define our V matrix and then our permutation matrix P, and we permute V by multiplying it by P from the left. And now you can see that 5 and 3 are swapped. In chapter 5, we will talk about LU factorization.